Hello friends, in this video we are going to discuss about Parseval theorem, or also known as Parseval identity. This is lecture number 7. This is lecture number 7 of integral transform. Okay, so here we're going to discuss about Parseval identity of Fourier transform. Okay, so there are two different identities: Parseval identity for Fourier series, but we are going to discuss about Fourier transformation, Parseval identity for Fourier transformation. So don't be confused. Okay, so it may be written in some other books, Parseval theorem for Fourier transformation. Okay, so Parseval theorem for Fourier transformation and Fourier series, two different terms. Okay, remember, before we start, please subscribe the channel, hit the thumbs up button if you like my videos, and also share with your friends, and don't forget to hit the bell icon so that you get notified when new video will be uploaded, right? And inspire me to create new contents for me. Okay, and if you have any suggestion, then let me know in the comment box. Okay, and link of all the previous lectures are given in the description box. So Parseval theorem for Fourier transform, let me write here: Parseval theorem for Fourier transform. So what is the theorem here? You see, if we consider that Fourier transform of two functions, Fourier transforms of two functions, f of x and g of x, small f of x and small g of x, are given by, suppose, respectively capital F of s and capital G of x, g of s, not x. That is capital F of, that means Fourier transformation of small f of x is capital F of s, and Fourier transformation of small g of x is capital G of s. And also if these two are the if capital F of s is the Fourier transformation of small f of x, and this is the Fourier transformation of small g of x, in that case what we can write according to this theorem, we're gonna get two results. Then we're gonna have two results. First one is integration from minus infinity to plus infinity, Fourier transformation of f of x, that is capital F of s, and the complex conjugate of g of s. So complex conjugate of g of s means the complex conjugate of the Fourier transformation of small g of x, right? ds, that's going to be equal to integration from minus infinity to plus infinity, small f of x, then complex conjugate of small g of x dx. So where we can say capital G of s is conjugate, it should be complex conjugate, right? So here we have to write complex conjugate. Okay, so what we have got here, this capital G of s is the complex conjugate of capital G of s, and this gs bar, and small gx bar is the complex conjugate of small g of x, right? So hope you have understood this. If you have the idea of the complex number, then you must you must know these things. So now the second thing is, the second result, if you replace this capital G of s by capital F of s, its conjugate of capital F of s, that means the capital F of s bar, and if you replace this one by this one, then this must be replaced by small f of x, conjugate of small f of x, that is small f of x bar, right? And if we do that, then we're gonna get the next result. So what is the result? Let me clean these things first. Okay, just wait. So then we're gonna get this result. And let me tell you why I am using this mod symbol, because let me tell you, suppose we have a complex number a plus ib. Okay, z is equal to a plus ib, so its complex conjugate gonna be given by a minus ib, and z into z bar, that means product of z and its complex conjugate, that gonna be given by a plus ib into a minus ib, that's gonna be equal to a minus a square minus ib whole square minus I square, that's gonna be plus minus 1, this one here, you see, a square minus ib square, product of this one and this one, right? So a square minus I square is I square is minus 1, so it's gonna be plus b square. So that's why what we have got, product of these two will be equal to a square plus b square, and this is nothing but mod of z, which is given by square of mod of z. Actually mod of z is root over a square plus b square, so if you square it on both sides, then you're gonna get mod of z square, right, is equal to this. So hope you have understood this concept. That's why when I have multiplied f of s and its complex conjugate, that is f of s bar, then it must be given by mod of that's going to be equal to mod of f of s square, right? So hope you have understood this. So now let me show you the proof of this results. So let me go to a new slide and let me tell you the proof. Let me show you the proof. So by the definition of inverse Fourier transform, right? So what going to be the definition of inverse inverse Fourier transform? Let me tell you it again. So we know that we have already got the Fourier definition of Fourier transformation. The definition of Fourier transformation of a function f, small f of x, is given by capital F of s, which is equal to minus infinity to plus infinity e to the power minus I s x f of x dx. That's what we have already got. Now you see, so if you take the inverse Fourier transformation, definition of inverse Fourier transformation, that means if you need to find f of x, then you have to write minus infinity to plus infinity, then this side is gonna be positive e to the power I s x, then instead of f of x we're gonna have here f of s ds, right? So hope you have understood this. And if this is the definition of inverse transformation of f of x, then its complex conjugate gonna be given by, then this positive this I gonna be here, if here we have positive, then it gonna be negative I s x, then f of s its conjugate ds. That's what we should get. So hope you know these things. If you don't know, then note it, pause the video and note it. So now let me clear this. So by definition we should get g of x minus infinity to plus infinity g of s e to the power I s x dx ds, right? So the if you take the complex conjugate of g of x, then what we're gonna get, then we have to take complex conjugate of capital G of s, that's gonna be g of s bar, and then e to the power plus I s x, its complex conjugate gonna be minus I s x, e to the power minus I s x ds, right? So now what we're gonna do, we're gonna multiply both sides by f of x, then we're gonna integrate again, right? And f of x into g of x bar, that is complex conjugate of gx, then again we're gonna integrate it from minus infinity to plus infinity dx. So on the right hand side we're gonna have this. Let me explain how. Now you see, we have multiplied f of x on both sides, then this e to the power minus I s x is written with f of x because this is a function of x now. So then we have integrated with respect to x, right? That we have integrated with respect to x. This integration with respect to s already on the right hand side once. So that's why when we have integrated after multiplication of f of x with respect to x, that's why on the right hand side one more integration comes, right? So hope you have understood these things. So now just wait, give me a second. So now what we're going to do here, you see, so we're going to write this. How? Let me tell you, because this is nothing but the definition of Fourier transformation of small f of x, which is nothing but capital F of s, right? So that's why we can replace it by capital F of x. So hope you have understood this. So then, and this ds is written here, right? Now or this result can be written this way. So first one is proved, first part of the theorem is proved. Now let us replace this capital G of complex conjugate of capital G of S by complex conjugate of capital F of S. And if you replace this G of S, then you must replace the G of X as well. It's gonna be replaced by complex conjugate of small f of x, right? So doing so, what we're gonna have, let me show you on the right hand side. Here you see, then replacing a small g of x bar, that means complex conjugate of small gx, by small f of x, complex conjugate of small f of x. So replacing capital G of S bar, that means complex conjugate of small g or capital G of S by complex conjugate of capital F of S, that means capital F of S bar. And doing so, what we're gonna have, here mod of capital F of S square ds. On the right hand side, we're gonna have mod of capital F of small f of x square dx. So integration will be there on both sides. This is number 2 is proved, right? So hope you have understood this.